Hello everyone, welcome to today's class. In earlier class, we were discussing about this fluid mechanics subject and we covered fluid statistics, then hydrostatistics, then we covered Bernoulli equation, continuity equation, and in all that we were neglecting the frictional losses. But today we will be covering the aspects related to when the friction losses are present and how to calculate the friction factor. And later on, we will be moving on to this instrumentation, that is venturimeter, White tube, and we will be solving numericals based on that. So let's start with today's class. So the first question is from GATE 2021 chemical engineering paper. This is question number 28. So the question is, water of density 1000 kg per meter cube flows in an horizontal pipe of diameter 10 centimeter at an average velocity of 0.5 meter per second. The following plot shows the pressure measured at various distances from the pipe entrance. Using the data shown in the figure, the fanning friction factor in the pipe when the flow is fully developed is dash. So over here you can see that we have been given a plot of pressure versus distance of entrance from the pipe. That is, given a pipe, we are measuring the pressure at this distance at 1 meter, 2 meter. Similarly, we are measuring it until 6 meter, and corresponding to each point we are getting the pressure values. So we are getting a plot of pressure versus x, and using this we have to find the fanning friction factor, that is F, when the flow is fully developed. So when we say the flow is fully developed, that means the velocity profile will remain constant, and as the velocity profile will remain constant, the friction factor will also remain constant when the flow is fully developed. So we'll be utilizing that information. That is, basically we'll be calculating friction factor for each of this section. And when the friction factor between becomes constant, that implies the flow is fully developed, and then we can find, and that friction factor we can report as the final answer for the fully developed flow. So let's take a look on the video solution of this question. Question number 28, GATE 2018. Question number 28 of GATE 2021 chemical engineering paper. Water of density 1000 kg per meter cube flows in a horizontal pipe of 10 centimeter diameter at an average velocity of 0.5 meter per second. The following plot shows the pressure measured at various distances from the pipe entrance. So over here we have been given a plot of the pressure measured versus the distance from the entrance of the pipe. And using this data shown in the figure, the fanning friction factor of the pipe when the flow is fully developed is dash. So in this question, we have been given a horizontal pipe of diameter 10 centimeter. So the diameter of the pipe is 10 centimeter. The average velocity in the pipe is 0.5 meter per second. Then the density of the fluid is 1000 kg per meter cube. And we are measuring the pressure within this pipe at a distance of 1 meter, 2 meter, 3 meter, 4 meter, 5 meter, and 6 meter, and corresponding to that pressure, we generate this plot of pressure versus distance. And then we have been asked to find the fanning friction factor in the pipe when the flow is fully developed. So using the data that has been provided, that is pressure and distance, we will find out that in which of this section the flow is fully developed, and corresponding to that section we will find the friction factor. and that will be our final answer for the fanning friction factor. So when we say fully developed flow, that means the velocity profile throughout the pipe will remain constant. That is, velocity profile remains constant, and velocity profile will remain constant. That implies the friction factor will also become constant. So friction factor constant. So we will find the friction factor in each of this section, that is 1, 2, 2, 3, 3, 4, 4, 5, 5, 6. And when the friction factor in any of these two sections becomes constant, that is, it will be same, that implies that the flow is fully developed. And for that section, whatever friction factor we got, that will be our final fanning friction factor, or the final answer. So the pressure loss due to this friction, we can write it as delta P by rho is equal to 2FLV square upon D, where F is the friction factor, L is the length of the pipe, or the length of the section, V is the average velocity, D is the diameter of the pipe, rho is the density of the fluid, and delta P is the pressure loss. So this fanning friction factor F we have been asked to find. So the F we can also write it as delta P upon L into D upon 2 rho V square. So this entire term, diameter, rho, and average velocity, will remain constant throughout the pipe. And this delta P we can calculate for each of this section. So ultimately the friction factor will become delta P. In each of this section, the length of the pipe will always be 1 meter. Length of the section will be 1 meter. So this distance is 1 meter. Again, this will be 1 meter. So length also we can calculate it as 1 meter. Then diameter, we can replace the value as 10 centimeter. So that will be 0.1 meter. 0.2, density is 1000 into velocity is 0.5 meter per second. So this will come around delta P into 2 into 10 raised to minus of 4. So we are having this equation correlating the friction factor with the pressure difference. So now we will be using that to find the pressure difference at each of this section, and corresponding that we will find the friction. So F, so between 1 and 2 we can write this F12 is equal to delta P. Delta P will be 1205 minus 1152, 1205 minus of 1152 into 2 into 10 raised to minus 4. So this will be 53 into 2 into 10 raised to minus 4, that is 0.0106. Now F23 will be 1152 minus 1112. So that is 40, 1152 minus 1112, 40 into 2 into 10 raised to minus 4. That will be 8 into 10 raised to minus 3. So now here we can see that the friction factor within the pipe is changing. So as we move ahead in pipe, the friction factor is decreasing. That means the velocity profile hasn't been fully developed yet. So now we will repeat the same exercise for the other section. That is, we can find F34. So F34 will be 1112 minus of 1074. That is 36 into 2 into 10 raised to minus 4. So it will be 7.6 into 10 raised to minus 3. So 1172 minus 1074 was not 36, or 38. 38 into 2 into 10 raised to minus 4 is 7.6 into 10 raised to minus 3. So now for this 4 and 5 section, we can write this F45 as 1074 minus of 1037. That is 37 into 2 into 10 raised to minus 4 will be 7.4 into 10 raised to minus 3. So also we can say that until here the flow hasn't been fully developed yet, since the friction factor is changing in each of these cases. Now for the last section F56, you can write it as 1037 minus of 1000 into 2 into 10 raised to minus 4 is it. So now it will be 7.4 into 10 raised to minus 3. For the last section, that is 5, 6, we can see that the friction factor is becoming constant. That implies the flow is fully developed, and we can write the fanning friction factor within the pipe, that is F, as the 7.4 into 10 raised to minus 3. So this is our final answer. And from the given option, we can select this option B, that is 0.0074 as the correct answer. Right now, we looked on this question in which we had to calculate the fanning friction factor from the plot given over here. So what we did was, from the from the given plot, we used this equation, that is for the pressure loss due to friction, given by delta P by rho is equal to FLV square upon D. And since in the plot we were given this correlation between pressure versus, let's say, length, and we had to find the friction factor. So we developed such a equation where F is the friction factor and delta P by L, we can call it as unknown, and rest all terms were constant. So from using this, we can say that the slope of this line can be this delta P upon L. So we calculated the slope for each of this section by calculating delta P by L. That is, for first section, it was 1205 minus 1152 upon 1. Then for second section, it is 1152 minus 112 upon 1. And finally, you can see that for some length, the friction factor, that is F, will become constant. And in this case, we observed that for this section 5 and 6, the friction factor became constant to a value of 7.4 into 10 raised to minus 3. So since the friction factor is constant, that means the velocity profile would be constant, and that implies that the flow is fully developed. And that is why we say that at this 5 and 6 section, the friction factor is 7.4 into 10 raised to minus 3 for fully developed flow. So that is why we selected our final answer as 0.0074. Now, let's take a look on the next question. So this question is related to Bernoulli's theorem, as well as it will utilize the concept of this friction factor to calculate the frictional loss. So the question states that two reservoirs located at the same altitude are connected by a straight horizontal pipe of length 120 meter and inner diameter 0.2 meter, as shown in the figure. A pump transfers the liquid of density 800 kg per meter cube at a flow rate of 1 meter cube per second from reservoir 1 to reservoir 2. The liquid levels in reservoir 1 and reservoir 2 are 2 meter and 10 meter respectively. Assume that the reservoir's cross-section areas are large enough to neglect the liquid velocity at the top of the reservoirs. All minor losses can be ignored. The acceleration due to gravity is 9.8 meter per second square. If the friction factor for the pipe flow is 0.001, the required power of the pump is dash. So in this question, we have been provided this diagram, and the diagram has this two reservoir 1 and reservoir 2, and we are using a pump to transfer the fluid from reservoir 1 to reservoir 2, and the reservoir 2 is filled up to a height of 10 meter, while the reservoir 1 is filled up to the height of 2 meter, and the length of the pipe is 120 meter, and it has an uniform cross section area. And for this given system, we have been asked to find the power required by the pump. And here we will be considering the frictional losses due to the pressure loss due to friction, that is delta P by rho due to friction we will be considering. So let's take a look on the video solution for this question. Hello everyone, we are solving question number 52 chemical engineering paper, and this question is related to the subject of fluid mechanics. The question states, two reservoirs located at the same altitude are connected by a straight horizontal pipe of length 120 meter and inner diameter 0.5 meter as shown in the figure. A pump transfers the liquid of density 800 kg per meter cube at a flow rate of 1 meter cube per second from reservoir 1 to reservoir 2. The liquid levels in reservoir 1 and reservoir 2 are 2 meter and 10 meter respectively. Assume that the reservoir's cross-section areas are large enough to neglect the liquid velocity at the top of the reservoir. All the minor losses can be ignored. The acceleration due to gravity is 9.8 meter per second square. If the friction factor for the pipe is 0.01, the required power of the pump rounded off to one decimal place is dash. So in this question, we have been given two reservoirs and we have been asked to find how much power will be required by this pump to deliver the fluid from reservoir 1 to reservoir 2, considering all the minor losses as negligible. Then all the other parameters we have been given, that friction factor is also 0.01, and ultimately we have to find the power required by the pump. So over here we have been given the length of the pipe is 120 meter, that is length is equal to 120 meter. The inner diameter of the pipe is 0.5 meter, let's call it as D, as 0.5 meter. The density of the fluid rho is 800 kg per meter cube. The flow rate in volumetric flow rate is 1 meter cube per second. Then we have been given the respective heights 2 meter and 10 meter, that is h1 is equal to 2 meter, h2 is equal to 10 meter. Let's just call it, this is reservoir 1, this is reservoir 2. Then gravitational acceleration due to gravity is 9.8 meter per second square, and the friction factor F is 0.01. So we can write the Bernoulli's equation across this point 1 and 2, which will give us this equation, P2 minus P1 upon rho, where P2 is the pressure for this reservoir 2 at the discharge of the pump, and P1 is the pressure at the suction of the pump. That is P2 minus P1 plus G Z2 minus Z1 plus half V2 square minus V1 square plus friction losses plus the work done required by the pump. This will be equal to 0. Now over here, the inner diameter of the pipe remains constant, that is 0.5 meter. That is the velocity at both this point 1 and 2 will be same. That is, we can neglect this term. Also, the P2 and P1 both are open to atmosphere. So we can also neglect this P2, and so they will be same, and we can cancel this first term also, that is P2 minus P1 will be 0. So now we are left with these three terms, and we have to find the power. For that we require the work done. So first let us calculate this friction loss. That is, this friction loss we can write it as 4FL V square upon 2D, where F is the friction factor, L is the length of the pipe, V is the average velocity, and D is the diameter of the pipe. Now over here we don't have this average velocity, so that we can calculate it as velocity as volumetric fluid upon area, that is Q dot upon A. So we can write this as 1 meter cube per second upon the cross section area of the pipe will be pi by 4D square. Diameter is 0.5 square. So this will come around 5.09 meter per second. So this is the average velocity Based on that, we can calculate the friction loss. That is HF will be 4FLV square upon 2D. The value of F we have been given as 0.01. Length of the pipe is 120 meter. Velocity we have calculated it as 5.09 upon 2 times diameter. Diameter of the pipe is 0.5 meter. So again we can solve this, and the friction loss we will be getting it as 124.359. You can check the units and it will be meter square per second square. Now we can replace this HF in the earlier Bernoulli's equation. So we have G into Z2 minus Z1, that is basically 10 minus 2, that will be 8 meter plus HF plus W. So HF we have calculated it as 124.35 plus work done is equal to 0. That implies the work done will be minus of 124.359 plus 8 into 9.81. So that you can write 8 into 9.81, and ultimately it will come around 202.7. The unit will be same as the HF, that is meter square per second square. Now in the question we have been asked to find the required power of the pump. So power we can write it as mass flow rate into the work done. So it will be mass flow rate, we can simply multiply this volumetric flow rate by density, that is rho into Q dot plus W. So density we have been given it as 800 kg per meter cube, and the volumetric flow rate is 1 meter cube per second, and then the work we found out is 202.7. So this will come around 1622, okay, 207 watt. No, this will be 162207 watt. In the final answer we can write it as 162.207 kilowatt. So yes, the final answer is 162.2 kilowatt. In this question, we use the mechanical energy balance or the Bernoulli equation to find the required power of the pump. In the earlier classes, we were neglecting the losses due to friction, that is the pressure losses due to friction, but now we were considering the frictional losses, and we calculated that using the Fanning friction factor in this question. Similarly, let's take a look on a few more questions related to the Fanning friction factor. So this is question number 36 from GATE 2017. So the question is, the following table provides 4 sets of Fanning friction factor data for different values of Reynolds number Re and roughness factor K by D. Which of the above sets of friction factor data is correct? So we will take a look on the video solution again. Number 36 of Reynolds number, we have been given this roughness factor K by D, and for each of this Reynolds number and roughness factor, we have been given this calculated Fanning friction factor for this 4 sets, set 1, set 2, set 3, set 4, and we have to find which one of the following 4 sets is the correct. So we have this plot of friction factor or the Fanning friction factor F versus Reynolds number. From that we can see that if the Reynolds number is less than 2100, that implies the flow is laminar flow, and when the flow is laminar flow, the friction factor versus Reynolds number line will be a straight line, and that we can write it as F is equal to 16 upon NRE. Then there will be a critical region between the Reynolds number 2100 and 4000, and then we will be having a turbulent region. Now in turbulent region and as well as critical region, we can see that with increase in Reynolds number, the value of the friction factor will decrease, and also friction factor will depend on the roughness factor, that is the ratio of K by D. And we can say that the friction factor will increase as the roughness increase. That is as K by D increases, the ratio increases, the friction factor will keep on increasing. So using this information, we will solve the questions. So first of all, we can use this information of laminar flow. So laminar flow is characterized by the Reynolds number less than 2100. So for this first and second case, the Reynolds number is less than 2100. That is, we can see that this side is laminar flow and this part is turbulent flow. Now for laminar flow, we can calculate the fanning friction factor as 16 upon NRE. So it will be for this for this case. So for laminar flow, this roughness factor won't play much role. So we can simply use this correlation and calculate the friction factor as. So for Reynolds number of 100, we can write that F will be 16 upon 100, that is 0.16. For Reynolds number of 1000, that is this point, we can calculate the friction factor as 16 upon 1000, that is 0.016. Now from the given four options, we can see that for laminar flow, in the set 1, we have been given that the fanning friction factor is 0.16 for Reynolds number of 100, and for Reynolds number of 1000, the fanning friction is 0.016. That is, this option can be correct depending on if these two are correct. Now for set 2, we can see that the friction factor for Reynolds number of 100 is 0.016. That is incorrect. So this set 2 is incorrect. And for set 3, again the friction factor are 0.16 and 0.016. That is what we have calculated. So this can be correct depending on these two values. Now set 4, the friction factor is not this 0.16 on 0.016. So that is it. The set 4 is also is incorrect answer. So right now we have two candidates for the correct answer, that is set 1 and set 3. That is any one of two can be correct. So now we will be using the other information based on this turbulent flow criteria. That is, as K by D or the roughness factor increases, the friction factor should also increase. So for this 10 raised to 5 Reynolds number, we have been given the roughness factor as 0. That is, the pipe is very smooth. And as we increase the roughness factor to 0.001, ideally the friction factor should also increase. So if the friction factor increases, that implies that that corresponding set will be correct answer. Now for set 1 and set 3, we can see the value of fanning friction factor in the table, and for set 1, for Reynolds number of 10 raised to 5, the friction factor is 16 into 10 raised to minus 5, and again for the same Reynolds number of 10 raised to 5 for different friction factor, that is 0.001, we have been again given the friction factor as the same, that is 16 to 10 raised to minus 4. That is, with change in the roughness factor, that is ratio of K by D, the friction factor is not changing in this case. However, from this plot, the friction factor should change as we increase the roughness factor. That is, set 1 is an incorrect answer because this wasn't changing. Now, if we take a look on this set 2, set 3, we can see that the friction factor is increasing as we increase the roughness factor from 0 to 0.01 for the same Reynolds number. That is, set 3 is the correct answer. That is, from the given four options, the option set 3 is the correct answer, because in set 1 we saw is we saw the set one we rejected because the friction factor was not changing with respect to Reynolds number for constant Reynolds number. In set 2, the calculated friction factor for the laminar flow for both this Reynolds number were incorrect. The set and in set 4, again the calculated friction factor for the given Reynolds number were incorrect. That is why we rejected the set 1, set 2, and set 4 as the correct answers. So from the given options, we can select option C, that is set 3, as the correct answer. So in this question, corresponding to different Reynolds number and roughness factor K by D, we were given this value of frictional factor or fanning friction factor, and we were asked to find which of the following set is correct. So what we can remember from this question is two things, that if the flow is laminar, that implies the friction factor will be 16 upon NRE. Then there will be some critical region, and then there will be turbulent flow. For turbulent flow, you can remember that with increase in Reynolds number, the friction factor will decrease, and also with increase in the roughness, that is the ratio K by D, the friction factor will increase. And this correlation between Reynolds number and friction factor can be characterized by this equation, that is F is some constant time Reynolds number raised to n, and n is, I think, for few of the cases you can take n as minus of 0.2. That is friction factor is equal to 1 upon Re raised to 0.2. So you can just memorize these two equations, the first one and the second one. And this is straightforward, that if roughness increases, then friction factor will be increasing. So we used all this information to reject the incorrect options from the given sets. So now let's take a look on one more question of this friction factor, and then we will take a look on some boundary layer theory questions. So this is question number 6 from GATE 2016, and the question is, for a flow through a smooth pipe, the fanning friction factor F is given by F is equal to M into Re raised to minus of 0.2 in the turbulent flow regime, where R is the Reynolds number and M is a constant. Water flowing through this section of pipe with a velocity of 1 meter per second results in a frictional pressure drop of 10 kilopascal. What will be the pressure drop across this section in kilopascal when the velocity of water is 2 meter per second? So we will again take a look on the video solution. Question number 6 of GATE 2000. To a section of this pipe with a velocity 1 meter per second, pressure drop across. As given in the question, we are having a pipe through which water is flowing, and if the velocity of the water is 1 meter per second, then the frictional pressure drop is 10 kilopascal, and if the velocity of water is 2 meter per second, then we have been asked to find the pressure drop. So first of all, over here for the turbulent flow, we have been given this fanning friction factor equation, that is M into Re raised to minus of 0.2. Now we know that in general the pressure drop can be written as delta P by rho is equal to FLV square 2FLV square upon D. So this is the friction pressure drop due to friction, and this F is the fanning friction factor. So what we can do is, using this equation we can find the correlation between F and we can find the correlation between delta P and velocity, and using that we can find our final answer. So this is, we can replace the value of F over here in this equation. So we will be getting delta P upon rho is equal to m r e raised to minus of 0.2 into m L v square upon d. Now Reynolds number, we know that it is given by rho v d by mu, where v is the average velocity, d is the diameter of the pipe, rho is the density, and mu is the viscosity. So this is, we can write this as m into rho v d mu raised to minus of 0.2 m L v square upon d. So over here this m is a constant, rho v mu, okay, this m would be over here. So m, rho v mu, L and d are constants, and only variable over here is this velocity, this and this. So that is, we can just define some another arbitrary constant k dash, and v is the variable, so it will be 2 minus of 0.2. This density will also be remain constant, so that is also included in this arbitrary constant k dash. So that is, we can write that pressure drop is proportional to velocity, that is average velocity raised to 2 minus of 0.2 is 1.8. Now we can use this equation to find the pressure drop at velocity of 2 meter per second. So using this we can write delta P2 upon delta P1 is equal to V2 upon V1 whole raised to 1.8. Now V2 we have been given as 2 meter per second and V1 is 1. This will become 2 raised to 1.8. So delta P2, or the frictional pressure drop for the second case, will become delta P1 is 10 kilopascal, that is 10 kilopascal into 2 raised to 1.8. So this we can solve, and we will be getting 34.82 kilopascal. So the pressure drop when the velocity of water is 2 meter per second is 34.82 kilopascal. So we can select option C from the given options as the correct answer. So in this question, we calculated the fanning friction factor for the turbulent flow given by this correlation, and then utilized it to calculate the frictional pressure drop for the given velocity. Now let's take a look on this question. So now the questions will be related to this boundary layer. So in this question, we have been given that consider an incompressible flow of constant property fluid over a smooth, thin, and wide flat plate. The free stream flows parallel to the surface of the plate along its length, and the velocity is constant. The velocity of the Reynolds number, the value of Reynolds number at a distance of 2 meters from the leading edge of the plate is 8,000. The flow within the boundary layer at a distance of 1 meter from the leading edge of the plate is dash. So over here we have been given a, let's call it a flat plate, and then at 2 meter, let's say if this is our velocity profile at 2 meter. For this velocity profile, we have been given that the Reynolds number at x equal to 2 is 8,000. So let's just consider this direction as x, and this is our velocity profile. And then in the question, we have been asked to find the flow within the boundary layer at a distance of 1 meter from the leading edge of the plate is dash. So if this is 1 meter, and if the flow, let's say, is given by such a profile, then what kind of flow is this that we have been asked to find? So basically what we can do is, for this given x of 1 meter, we can find the Reynolds number, and for a flow through the flat plate, we can remember this correlation that if the Reynolds number is less than 10 raised to 5, that implies the flow will be laminar, and if it is greater than 10 raised to 5, then we can say that the flow will be turbulent. Now, so Reynolds number for flow over the flat plate, we can write it as rho v x upon mu. So rho is the density of the fluid, v is the average velocity of the fluid, and x is the distance from the leading edge of the plate. So if this is the end point of the plate, or if this is the starting point of the plate, then the distance from this starting point of the origin, we call it as x, and this point is known as the leading edge of the plate, and mu is the viscosity. So since the flow is incompressible and the flow of constant property, that is, we can say that the density and viscosity will remain constant, and also we have been given that the velocity is constant. That implies these three terms are constant, and we can say that Reynolds number is proportional to the distance from the leading edge of the plate. Now we have been given that the Reynolds number is 8000 for a distance of 2 meters, that is RE2. So we can find the ratio of Reynolds number 2 meter and 1 meter, and from that we can find the Reynolds ratio. From that we can find the Reynolds number at 1 meter, that is RE2 upon RE1 is equal to 8000 upon x, and this, so this is, we have to find Reynolds number, and this will be equal to the ratio of their distances x, that is 2 by 1. So 8000 was the Reynolds number at 2 meter, and R is the Reynolds number at 1 meter. So from this we can get that the value of Reynolds number is 4000. And since this Reynolds number is less than 10 raised to 5, we can say that the flow is laminar. So we can select option A as the correct answer. So now let's take a look on similar question. So this is again question number 6 from 2019, and here we are given that for a fully developed turbulent hydrodynamic boundary layer for flow past a flat plate, the thickness of boundary layer increases with distance x from the leading edge of the plate along the free stream flow direction as dash. So basically, in this question, we have been asked to find the relation between delta versus x. So if this is our flat plate, this is our leading edge of the plate, and this is the distance x from the leading edge of the plate. And if I have to, let's say, draw velocity profile for such, so this is the velocity profile, then this distance is known as delta, and in this question we have to find the correlation between delta and x. So for turbulent flow, for flowing over the for flow over a flat plate, for turbulent flow, we can remember this correlation that delta is equal to 0.376 times of x upon RE raised to 1 by 5. So this is the constant that you need to remember in fluid flow subject as well as in heat transfer. So from over here, the Reynolds number will be for the flow over this flat plate, that is basically it will be again rho v x upon mu, where v is the average velocity, rho is the density, and mu is the viscosity, and again these three terms are constant. So we can replace this value in this equation, and we can get this 0.376 x upon, so these three are constants, so let's just call it as some arbitrary constant k dash, and x raised to 1 by 5. Again, this is a constant, so we can write that delta is proportional to x raised to 1 minus of 1 by 5. That is, delta is proportional to x raised to 1 minus of 0.2. That is, delta is proportional to x raised to 0.8. So that is from the given options. We can select option D as the correct answer. That is, the thickness of the boundary layer increases with distance x from the leading edge of the plate along the free stream flow direction as x raised to 0.8. So this is the correlation that you need to remember, and based on this we can find that how this boundary layer thickness will vary with distance x. So I guess this much is sufficient for today. In the next class, we will be covering these questions related to this venturi emitter and pitot tube. And later on, we can see the numericals related to the flow through the packed beds or flow through all the pump characteristics, all those questions. Meanwhile, if you have any questions in the questions discussed today in the class, you can write it in chat box or just unmute yourself and speak up. We can solve it now. If you don't have any doubts, we can end today's session. So until now, what we have done is we have studied the basic introduction of the course, that is fluid mechanics. So what is fluid? So fluid is any substance that deforms under the application of the shear force, that is a permanent deformation is obtained, and fluid at rest cannot sustain a shear stress. That is how we define the fluid, and this property of the fluid due to which it resists the shear force is known as the viscosity of the fluid. And to find the viscosity of the fluid, we have this power law model or the Newton's law of viscosity, which captures the relation between the shear stress and the strain rate, and that proportionality constant is the viscosity mu. Similarly, for non-Newtonian fluid, we have this power law model. Later on, we covered this fluid statistics part, and then we had take a look on this mechanical energy balance or Bernoulli equation, then continuity equation, and also the different kind of losses, that is the frictional losses through the when the fluid is flowing through any pipe. Okay, so we can end today's class. I guess this will be sufficient. Thank you for joining.